this video, we're going to be talking about Lagrange multipliers, and in this particular problem, we've been asked to find any extrema of the function f of xy equals x squared y plus x plus y, subject to xy is equal to 4. So when we see this kind of language, find extrema of this function subject to another function, we treat this first function as our original function, the function that we want to find extrema of. We call this second function the constraint equation because this first function is subject to or constrained by this second equation. When we see language like this, we're going to be using Lagrange multipliers in order to find the extrema of this function. The process that we're going to follow is always going to be the same, and the first thing we want to do is take our original function f of xy and find the first order partial derivatives. So we're going to find the partial derivatives of f with respect to x and with respect to y. So the partial derivative of f with respect to x, remember we treat y as a constant, we take the derivative with respect to x. So if we treat y as a constant, then the derivative of x squared y is going to be 2x y. The derivative of x will be 1. The derivative of y, since it's a constant, will be 0. So the partial derivative of f with respect to x is 2xy plus 1. The partial derivative of f with respect to y, we treat x as a constant, take the derivative with respect to y. So if x is a constant, then the derivative of x squared y is just going to be x squared, the derivative of x will be 0, and the derivative of y will be 1, so we'll get x squared plus 1. Now what we're going to do is take the partial derivatives of the constraint equation, but before we do that, we need to always turn our constraint equation into a function g of xy. The way that we do that is by collecting all of the terms on one side of the equal sign, making the value on the other side of the equal sign 0. So in order to do that, we'll just subtract 4 from both sides, and what we'll get is xy minus 4 is equal to 0. So we just subtracted 4 from both sides. Now that we have this equal to 0, we'll replace the 0 with g of xy, and we'll say g of xy is going to be equal to xy minus 4. So that's how we turn our constraint equation into a function for g. Now we want to take partial derivatives of g with respect to x and y. So the partial derivative of g with respect to x is just going to be y. The partial derivative of g with respect to y is just going to be x. And now that we have all 4 of our first order partial derivatives, Lagrange multipliers tell us that we can set up these two equations. We're going to set corresponding partial derivatives equal to one another. So we're going to set the partial derivative of f with respect to x equal to the partial derivative of g with respect to x. All we do here, so we say 2xy plus 1 is equal to, now we'd set it equal to y, but we want to multiply y by the Lagrange multiplier lambda. So that's where the Lagrange multiplier process comes in. We want to set this equal to lambda y. So we set these two equal to each other. We just multiply the partial derivative of g by lambda. Then we'll set up our second equation here, and we'll say x squared plus 1 is equal to x, but we have to multiply that by lambda, so we're going to get lambda x. Now what we want to do here, now that we have lambda in both equations, we want to solve one of the equations for lambda and then make a substitution into the other equation for lambda. So if we go ahead and solve this first equation for lambda, the way that we would do that is by dividing both sides by y. We would get lambda is equal to 2xy plus 1 all divided by y, because we divide by y here to get lambda by itself, and we'd have this left-hand side divided by y. Now that we have this value for lambda, we're going to take this value for lambda and plug it in for lambda right here. And when we do that, this equation is going to become x squared plus 1 is equal to x times lambda here, which is 2xy plus 1 all divided by y. And now what we want to do is solve this equation for y in terms of x. So we'll go ahead and simplify this fraction first. We're going to get x squared plus 1 is equal to x times, we'll say 2xy over y plus 1 over y. Because we have two terms in the numerator, we can separate them into two separate fractions, each over the original denominator of y. When we do that, we're going to get y to cancel with y right here, and so then we'll end up with x squared plus 1 is equal to, distributing the x, we get x times 2x, or 2x squared, plus x over y. Now, to get rid of the fraction, we'll multiply through every term on both sides by y, because that'll get y to cancel with this y here. We just have to multiply the y by each of the other three terms. So then we're going to get x squared y plus 1 times y, or y, is equal to 2x squared y plus x. So now we've gotten rid of our fractions. We want to get all the terms involving y on both sides. So we're going to have this term here, y. Then if we subtract 2x squared y from both sides, we have an x squared y minus a 2x squared y gives us a negative x squared y is equal to x. Now if we factor out a y from the left-hand side, we're going to get y times 1 minus x squared is equal to x. And then if we divide both sides through by 1 minus x squared, we can solve for y and say y is equal to x over 1 minus x squared. Now that we have a value for y in terms of x, we want to plug this value into our constraint equation. So here's what we're going to do. We're going to take this value here that we found for y, x over 1 minus x squared, and we're going to plug it in for y right here. And so then we're going to have an equation in terms of x only. We'll be able to solve for x. So we're going to get x times, here's where we plug in y right here, x over 1 minus x squared. That's going to be equal to 4. Now we want to solve this for x. So what we're going to get is x squared over 1 minus x squared is equal to 4. When we distribute this x, we'll multiply both sides by 1 minus x squared and get 4 times 1 minus x squared. Now we want to distribute the 4, so we'll get x squared equals 4 minus 4x squared. Adding 4x squared to both sides, we get 5x squared equals 4. Dividing both sides by 5, we get x squared is equal to 4 over 5. And taking the square root of both sides, we're going to get x is equal to positive or negative 2 over root 5. So we have two values of x, both positive and negative 2 over root 5. We want to take these values for x and plug them back into our equation for y so that we can find corresponding values for y. So we're just going to take this value of x from the right-hand side, and we're going to plug it in for x here and also here. And so when we do that, we're going to get y is equal to, let's start with positive 2 over root 5. We're going to get 2 over root 5 in the numerator, divided by 1 minus quantity 2 over root 5 squared. If we plug in the negative value, we're going to get y is equal to negative 2 over root 5, divided by 1 minus negative 2 over root 5 squared. So when we simplify here, we'll start with this positive value, positive 2 over root 5. When we square that, we're going to get 4/5. So this 2 over root 5 quantity squared is going to be 4 over 5. So then we have 1 minus 4/5 in the denominator. If we change this 1 to 5 over 5, now we have a common denominator, and what we get is 5/5 minus 4/5, or 1/5. So the entire denominator then becomes 1 over 5. So we can say y is equal to 2 over root 5, the numerator, and then instead of dividing by a fraction, we can multiply by its reciprocal. So we'll multiply by 5 over 1 instead of dividing by 1 over 5. So 5 over 1. Then we want to recognize that 5 is the same thing as the square root of 5 times the square root of 5. And the reason that we do that is because it allows us to cancel a square root of 5 and a square root of 5, and the resulting value of y then is y equals 2 square root 5, because we obviously don't need to write the 1 in the denominator. So y equals 2 square root 5. We'll come back to that in a second. But if we look at the value negative 2 over root 5, here when we square this value, the negative signs will cancel, and this is still going to be here positive 4/5. So again, we get 5 over 5 minus 4 over 5, or the entire denominator is 1 over 5. So then we can say y is equal to negative 2 over root 5, and then instead of divided by 1 over 5, we multiply by 5 over 1. And then we call 5 the square root of 5 times the square root of 5, and we cancel the square root of 5 from both the numerator and denominator, and we say y is equal to negative 2 root 5. Now what we can say is that when we match these values of y with the corresponding values of x, when we plugged in x is equal to positive 2 over root 5, we got y equals 2 root 5. So we can say that that coordinate point is positive 2 over root 5, comma 2 root 5. When we plugged in negative 2 over root 5, we got negative 2 times root 5. So the value there then is negative 2 over square root 5, comma negative 2 square root 5. Now that we have these two critical points, we want to use the second derivative test to see whether or not either of them represent an extrema for the function. So the way that we're going to do that is to use this value here, d, and what we need to do is find the second order partial derivatives of the original function, so the second order partial derivative with respect to x, with respect to y, and the mixed second order partial derivative, so that we can plug those values into this equation for d, and then whatever value we get as a result, we'll evaluate that at both of these critical points. So starting here with the second derivatives, in order to find the second order partial derivative of our original function f with respect to x, we're going to start with the first order partial derivative with respect to x and take the derivative with respect to x again. So if we take the derivative of 2xy plus 1 with respect to x, the result there is just going to be 2y, because this 2y will act like a coefficient on the x variable, and the derivative of 1 of any constant is going to be 0. Then our second order partial derivative with respect to y, we'll start with the first order partial derivative with respect to y and take the derivative of this with respect to y. Well, there are no y variables here involved, so when we take the derivative of x squared plus 1 with respect to y, the result is just going to be 0. And then if we want to take the mixed second order partial derivative, so the mixed second order partial derivative, we can start with either of the first order partial derivatives and then take the derivative with respect to the opposite variable. So for example here, we took the partial derivative of f with respect to y. Now we want to take the partial derivative of this with respect to x. Doing that, of course, will just give us 2x plus 0, or 2x, so we can say that the mixed second order partial derivative is going to be 2x. And notice that if we had done it the opposite way, started with the first order partial derivative with respect to x, and then taken the partial derivative of that with respect to y, we would have said the derivative of 2xy plus 1 with respect to y is just 2x plus 0, or 2x, so we get the same thing either way. Now, with all of these values together, we want to plug them into our equation for d. So we're going to get d of x, y, lambda is going to be equal to the second order partial derivative with respect to x, which we know is 2y, multiplied by the second order partial derivative of f with respect to y, which we know is 0. And then we're going to subtract from that the mixed second order partial derivative squared. So we're going to take this 2x value and we're going to square that. And then we want to simplify this as much as possible. Obviously, 2y times 0 is going to give us 0. So here we're going to have 2x quantity squared is a 4x squared. So we end up with a negative 4x squared. So we have this expression then for d of xy lambda is equal to negative 4x squared. Now what we want to do is evaluate d at each of these critical points. The value that we get as a result of plugging the critical points into d is going to tell us whether or not either of these critical points represent an extrema of the function. So we'll start with this first critical point. We'll plug that in. So we'll go ahead and say d of 2 over root 5, 2 root 5, and then lambda is going to be equal to, we have negative 4, and then we plug in the value of x, which is 2 over root 5 quantity squared. The result there, here, when we square 2 over root 5, we're going to get 4 over 5. When we multiply by a negative 4, we're going to get negative 16 over 5. If we do the same thing with the second critical point, so we'll say d of negative 2 over root 5, negative 2 root 5, and lambda, we're going to get negative 4 times quantity negative 2 over root 5 squared, which is going to give us a positive 4/5 again times a negative 4, so again negative 16 over 5. Now what the second derivative test tells us is that if d is less than 0, if d is negative, then the critical point at which we evaluated d represents a saddle point of the function. On the other hand, if d is equal to 0, the second derivative test is inconclusive. And then if d is positive or greater than 0, we have to go back and look at the second order partial derivative with respect to x. So that would be this value right here. We would evaluate this expression 2y at the same critical points. And then depending on that result, we would say that the critical point represented a local maximum or a local minimum. So if d is greater than 0 and the second order partial derivative of f with respect to x, so we'll say f sub x, if that is also greater than 0, then the critical point represents a local minimum. If d is greater than 0 and the second order partial derivative of f with respect to x is less than 0, then the critical point represents a local maximum. In our case, notice that both critical points produced a negative value for d, which is this first case here, which means that both critical points represent a saddle point of the original function f of xy subject to the constraint equation xy equals 4.